All right, so welcome everyone to the last talk of today by Omri, Ben-Eliezer, who is going to tell us about adversarially robust streaming algorithms. I guess the principle is that just because you are paranoid doesn't mean they are not out there to get you, right? Sorry, that was supposed to be a funny joke. I guess it was. All right. Okay. Please ignore everything.
I assume the audience is adversarial.
Yeah. Streaming algorithms for the paranoid. All right.
Okay. So I actually not assume that the audience is adversarial, but rather tired. So since it's the last talk of the day, it won't be that heavy technically. I think there is one definition that I want you to understand and one proof that I want you to understand. And the rest of the talk is kind of like very high level, kind of just to give you a sense of what kind of techniques people are using. Okay. So let's start with the basic streaming model. Let's be the same one that I talked about in the first talk. But here it's not about graph streaming, it's about functions where the output is, let's say, some real number. So the basic setting is we have a stream of updates. Each update is some object of a world of size n. And with each update, we can insert some amount of elements from this, units from this object, or remove some amount of units from this object. And the goal is to compute, so usually you can only efficiently approximate some function over the stream. So it's actually basically so that each update updates some frequency vector over the world. And we want to compute some function over the frequency vector of the world. For example, the number of distinct non-zero elements in this vector, the Euclidean norm, the entropy, the set of heavy hitters, which is actually not a real output, but also related, and so on. So this is how it looks like. We have the world. It sends the algorithm some amounts of units of some element. Then the algorithm needs to process it. So as usual in streaming, we want the amount of space to be small. And then after the first element is inserted, another element, well, maybe this time some element is deleted some amount of times, and the algorithm processes it, and so on. We generally assume in this talk that the length of the stream is something that is like the same order of magnitude, maybe polynomial in the size of the universe. Both of them are very large, so we want the streaming algorithms to depend ideally polylogarithmically in M and N. Maybe polynomial in epsilon is fine. And one type of functions that we will be interested in are FP, the FP moments. For example, the number of distinct elements is the F0 moment. It's defined like this. And the Euclidean norm is the square root of the F2 moment. So F0 and F2 are two basic functions that we will be interested in throughout the talk. Okay, and there are very efficient randomized streaming algorithms, as probably many of us know, for this kind of problems. So for the number of distinct elements, F0, F2 estimation, entropy, and so on, for all of these problems, we have streaming algorithms with space complexity that depends polynomially on epsilon, and then polylogarithmically on n. And for all four of these problems, deterministic algorithms are inefficient. So the space complexity is either linear in n or at least square root of n. In all cases, it's pretty bad. But there is also some common problem for all of these results that we see here. And this is that all the proofs of all of these results, of all of these bounds, actually assume that the stream is fixed in advance. what we mean by fixed in advance. It means that, so before we saw that the world only sends stream updates in the direction of the algorithm, but in many realistic scenarios, it can't really be the case. There is some feedback loop between the world and the algorithm. So for example, here we see an adversarial world. Again, it sends the first update in the stream. And then the algorithm, again, needs to be small space. It processes it. And now, okay, so we think of the algorithm as a tracking algorithm. It continuously kind of generates outputs. So it generates the first output. But then in this model, the world can store the output. And the next update that the world sends can depend on this output. In general, we assume that the adversary, the world, is computationally unbounded. It can memorize everything. It's stronger computationally than the streaming algorithm, which is supposed to be a bounded space. In this one. All right. Let's go back to one of the most important techniques in streaming. This is linear sketching, and we saw it in the first talk today. So kind of perhaps the work that kind of systematically started the field of streaming, the work of Alon Matias and Szegedi, where basically they came up with this technique, and they showed that it produces an efficient streaming algorithm for example, for F2 estimation. And the idea, so the technique is basically to generate a sketching matrix, and for the purpose of, and basically the idea is that if we multiply the frequency vector by the sketching matrix, the L2 norm of S, the sketching matrix times V, is equal to the L2 norm of, is in expectation equal to the L2 norm of the frequency vector itself. So this is an unbiased estimator, and basically, so here you see it's the one-line proof that this is an unbiased estimator, and this uses the fact that in order to, okay, so basically the expectation of this of the norm squared is, it turns out to be the sum of the elements of the frequency vector squared, plus this sum that includes products of pairs of elements of the sketching matrix. So basically the proof of this, that this is an unbiased estimator, uses pairwise independence between entries of the same row of the matrix. You actually need fourwise independence for the variance. I didn't include the computation here. But there's an issue. So this is in the static world. In the adversarial world, there's an issue. So, I mean, in the adversarial world, the world can try to learn the sketching matrix, because it can try to see like what outputs it sees from the algorithm, and if it detects correlations. So this, assuming that the expectation of this product of pairs of elements is zero, it's no longer true because we don't have independence. It was only true when we had independence, and then we could, and then the expectation of the product was the product of these expectations, which was zero. So this computation is no longer true. This is no longer an unbiased estimator. So linear sketching breaks down. And indeed, the attack by the first systematic attack on linear sketches, which is by Hart and Woodruff, basically does something like this. So they show that you can get, for example, a constant factor and any polynomial factor approximation assuming the adversary has sufficiently many rounds to attack. Yeah, so they basically learn slight correlations, they boost them, And this way they can generate vectors that are approximately in the row space, and they peel them one by one until we have a constant dimensional sketch, and then you can break it even non-adaptively. Right. So linear sketching, perhaps the most used, or one of the top 2 or 3 most used techniques in the streaming literature, is just completely not robust, which is of course an issue. Okay, I didn't tell you why we care about robustness. It may be obvious to some of you, but I mean, many of the systems in our world that use streaming algorithms kind of interact adaptively with the world. So in some cases, so for example, the case that we see here on the left, we can actually have actual adversarial attacks. So this example on the left demonstrates an attack that 2 security researchers ran on some server, and they were able, by learning the internal randomness of the server, they were able to cause a denial of service with very little interaction. So kind of what Hart and Woodruff did in theoretically, it can also be, of course, done practically. And of course, these are like good hackers, and we don't know what actual adversarial people are doing to systems like this. So actual adversarial attacks are a problem, but a lot of the interactions that we have in our world are like adaptive, even if they are not fully adversarial. So for example, if Google runs some streaming algorithm, compresses the data in some way so as to rank different websites, there are some search engine optimization services which try basically to optimize the ranking of certain websites, and they are strategic. They're not adversarial, but they are strategic, and Google wants to be robust to this strategic behavior. There are many other examples. So, for example, if you have a model that interacts with users, and the way that it optimizes over time uses some adaptive optimization methods. So, for example, gradient descent, where the steps that it decides to take depend on the data that it sees. So there is some feedback loop, and we need guarantees for this kind of setting. So in modern settings, we need adversarial robustness. In many cases, it might not be the case that the adversary is actually adversarial, but we need some sort of guarantees. Okay. So in the second part of the talk, any questions about the model?
In other words, you can be adversarial even if you don't need to.
Right. I mean, you can be adaptive. Yes, adaptive to the outputs. So I mean, yes, if a user interacts with the database and wants to extract some data, so it can make some query to the database, and then the database answers. And obviously, I mean, the user can make another query that is like depends on this. On the answer. So I don't know if we interact with Google Maps to get driving directions. I mean, this is kind of an interactive discussion, and obviously the way we drive affects others. So it's kind of we affect also the outputs of the algorithm in some sense. Sorry, it depends who you think of as the algorithm and who is the stream, but there is some interactivity here. Okay, so we've seen that linear sketching is completely not robust. So the next question is, what can we do to make streaming algorithms robust? Or whether there are techniques to make streaming algorithms robust. So the good news are that there are some techniques. They work in many cases, not always. They don't always work very well, but in many cases they work pretty well. So the one definition and proof that I would like to show is related to sketch switching. This is the first framework that we will see to make kind of static streaming algorithms that work in the classical regime. to turn them into ones that are robust against adversaries. So this is like the simplest framework. It's also the weakest, and it's probably the only one that I can completely show kind of the idea in a way that is actually understandable. So I'll maybe say a few words about the next two frameworks, which are a bit more efficient, but also more, substantially more efficient, but also a bit more complicated. And there's also a combination of these two more advanced techniques. Okay, so let's look into the sketch switching technique. This is joined with Rajesh Jairam, with David, and with Eilonia Gift. So basically, let's recall what standard streaming algorithms give us. So the guarantee that they give us is that for any fixed stream, if I give the algorithm a specific stream of updates, so the algorithm will return an output that is correct for this specific stream. And what we're going to do is we're going to run a number of different copies of the algorithm that is suitable for the classical world. And we're going to switch between them from time to time. Okay, so, and this number is, I'll call it lambda for now. We'll give it a name afterward. And the idea is that we run simultaneously all of these copies of the static algorithm. Each time that the stream gives us another update, we give it as an input to all of the copies, but not all of the copies send an output to the adversary. What we do is there are actually two copies that are kind of more active at any given moment. One copy that we call the active copy, and another copy that is maybe not active, but this is the copy that actually provides the output to be seen by the adversary. So basically, in each time, the active copy monitors the copy that provides an output to the adversary. And basically, the role of the active copy is to detect whenever, and this output by the one that provides the output to the adversary, this output is frozen. So the role of the active copy is to determine when this frozen output is no longer valid. Any questions about? So this, I think, the next few slides are the only thing that I actually want you to understand. Can be confusing. So if there are any questions, take special care to ask. What do you mean by hybrid argument?
Like you said that an adversary could be fully adaptive. So why are you limiting that?
So the adversary is adaptive to the outputs of the algorithm. What it is going to see is like a series of like the frozen outputs of this copy, and then once the active copy decides to switch, so the active copy becomes and then you have like a sequence of the frozen. So you get the frozen output of this copy for some time until this copy decides to switch, and so on. So this is what the adversary can actually adapt to. It's a sequence of frozen outputs. And they didn't say anything, obviously, if we set, for example, lambda to be m, to be the length of the stream, so we can just use a new copy for each incoming update, and because this copy was never seen by the adversary, it can be. So it's exactly the same as the static setting. So obviously, if we took m copies, we would be able to provide the guarantees to always give correct output. So the game is like to replace m with something that is more meaningful. Somehow depends on the problem.
When you're trying to say get an estimate of some statistic, and you're doing that against some optimal against the true statistic, I guess, right? And is that true statistic? Does it matter if the true statistic is something that the adversary has to compute or not? It's a question of whether or not the adversary just can wait till the end and get the right optimal thing, or anybody can, or does the adversary itself have to play the game?
Yeah, so the adversary provides us with the stream, and we need to return correct answers for the stream that the adversary provides.
Yeah, I understand. I guess it's just, when you're measuring approximations, is it, I guess, what is, the opt is the true opt, I guess, or something, the true statistic.
Yeah, so it's, I don't know if it satisfies you, but we are required to provide an output that is correct for the specific stream that the adversary provided adaptively. I mean, it could be adaptive, but we need to be correct on this adaptive stream.
Generally, there's some estimate, right?
There's no like underlying truth. It's not like a statistical model. It's a purely adversarial model.
Oh, this is okay.
I mean, it could be interesting to look at relaxations. Where we have a statistical model, maybe, but this particular model, without any further assumptions, it's just purely adversarial. So yeah, we don't have any problem here. All right. So yeah.
Sorry. So how does the algorithm know whether the output is incorrect? Is it compared to the active copy, or?
So can you repeat the question?
How does the algorithm know whether the frozen output is incorrect without revealing information about the active copy or any future copy?
So the algorithm knows whether the frozen output is. So there is a copy whose role is basically to determine whether okay. And so the active copy, we ask it to be sufficiently accurate. So let's say if you want to do 1 plus epsilon multiplicative approximation, so we ask the active copy, actually ask all copies to be 1 plus epsilon over 10 accurate on a specific stream, and we tell later what this specific stream is. And once it knows that, so it is very close to the actual output, and once it figures out that the actual output is, so what the output that this active copy produces is more than, I don't know, 1 plus epsilon over 2 away from the frozen output, so it figures out that it needs to switch. So maybe this will be the last question.
So maybe this is obvious, but so the reason why we are basically updating the visible copy to the active copy is basically we are expecting that with each new run of the algorithm we are learning something more. So this is a better copy.
So the thing is that, I mean, at some point you need to switch, because this otherwise this output will just be frozen forever. I mean, it's at some point it's going to no longer be valid. So I mean, you have to switch, and the active copy decides where to switch.
But the lambda copies of the algorithm, they are independent runs.
Yes, and lambda will depend on it's a structural parameter of the problem. We'll see it now. Okay, so the structural parameter of the problem is called the flip number. And this is defined as follows. So we have the function that we want to compute, let's say the number of distinct elements. And the flip number of this function with respect to epsilon and this length of the stream is the maximum possible number of significant multiplicative changes along the stream. The maximum number of 1 plus epsilon changes along the stream. So if, for example, we have functions number of distinct elements, and we are in an insertion-only world, so the number of distinct elements in the end of the stream can be at most m or n, doesn't matter, because they're of the same scale, and it's a monotone non-decreasing function. So the number of 1 plus epsilon jumps that it can do is log of n in base 1 plus epsilon, which is of order log n over epsilon. So the flip number in this case is log n over epsilon. And the sketch switching framework, what it does is it takes a classical algorithm. It takes as a black box a classical an algorithm for like classical streaming, classical computation of f that provides tracking, which means it provides output at any given time. And it turns this, using the framework that we've seen, into an algorithm that is adversarially robust. And the space is, I mean, the number of copies that we maintain times the space of a single copy.
Can we just make sure that I understand the idea of the previous slide? You're sort of running these lambda algorithms in parallel, maintaining their memory, and you're outputting the output of the, I don't know, active or whatever, or there are two that are.
Yeah, the frozen one, yes.
The one that in the future you are not outputting, so they cannot be, they are not leaking anything.
Okay, so we've seen that the flip number typically in insertion only settings where we only insert elements, it's typically the case that the function that are going to be monotone and decreasing, so the flip number is going to depend. So I want to remind you that the overhead that we have for the algorithm is the flip number. So when the overhead is log n over epsilon, it's not that bad, at least for our context. We don't really care about being optimal. We care about being maybe polylogarithmic in the size of the universe and the length of the stream. So in many insertion-only problems, we have some overhead. So this framework is not going to produce something optimal, but maybe not too bad. But what can we say about insertions and deletions? So this is called the turnstile model. Hasn't seen this before. Can
very small numbers, you can go up and down.
So this is an example, and what flip number will it give? And length of the string. So each time we undergo a multiplicative change of infinity, so flip number is very bad. And I mean, this framework doesn't give anything meaningful. That's unfortunate. Yeah. Maybe before we continue to other frameworks, I actually want to tell you to complete the proof. I mean, I didn't tell you about the proof, although we talked a lot about this framework. So for the proof, I need to specify what stream. So for each copy for copy AI, let's say that this copy is active at the current time, I want to specify exactly what stream it needs to be correct on. So the stream is the stream that is generated by the interaction between all of the past copies between A1 up to I-2 and the adversary, because at all of these times, this copy was just kind of a future copy. It didn't participate in the interaction in any way, so the adversary knows nothing about this copy until A sub I-1 becomes the frozen copy. And then, so this is what I call the A sub I limits part. And then we want the active copy to be correct on the following remainder of the stream of length m. We just assume that the frozen output is going to be this way forever. And we can assume the adversary to be deterministic. This is standard application of Yellow's minimum principle. Okay, so this is the stream that it needs to be correct on. It turns out that this is enough for this framework. Okay, so this is the only result that I wanted to fully present to you. So if there are questions, we'll take them now, and if not, we'll continue running. Okay, so let's continue. All right, so this is a framework that gives an overhead of the flip number, So since, for example, that in insertion only, it might not be that bad, but in turnstile, in insertions, deletions, it doesn't give anything meaningful because the space complexity is going to be linear, even more than linear in the length of the stream, so we need something better. And there has been a sequence of better frameworks. One of them is based on differential privacy. This is work by Hasidim, Kaplan, Mansur, Matthias, and Stemmer. And there has been another framework that doesn't optimize the dependence on the flip number, but it shaves off one epsilon factor, which is good for insertion-only purposes. This is a very clever framework by David and Samson Joe. And there's also actually a best of both worlds kind of framework. And there's also some lower bound that I'll mention, I'll discuss a bit later. Okay, let me maybe quickly tell you how, yes?
Why doesn't the lower bound contradict the best of both worlds?
Yeah, so here I hid the dependence on epsilon. I wanted to say that the dependence on the flip number in some cases can be a square root of lambda. So yes, it hides some epsilon factor.
So you don't know how to handle these cases where you go up and down,
with these generic frameworks, we'll get to it. I mean, the answer, yes, we don't really know how to handle them. We have some improvements of the generic frameworks, but they're rather mild. So the biggest open problem in this area is to, for example, to do robust F0, so robust distinct elements, or robust F2 estimation with something that is much better than we know slightly better.
So in the lower bound, that it's like lambda. Is lambda very large, like polynomial in M?
Sorry, so it can be M. I mean, we've seen that it can be M.
Okay. Yeah, but you said for specific problems, and we don't know if for the specific problem.
Oh yeah, yeah. So this lower bound is for a problem that was not a streaming problem that was studied in the literature before. It's a problem that was kind of imported from adaptive data analysis. So it was an artificial problem for the purpose of showing that this is static.
But there is pretty large.
It's polynomial in M. It's not M. Okay. I think it's M to the 2/5 function. Yeah. But for the string problems that you care about, F0, F2, it's N. So it could be N. So can be that. Okay. So let me try to just give you a rough idea of how these improved frameworks look like. So the differential privacy framework, instead of maintaining lambda many copies, it only maintains roughly square root of lambda many copies. And it has two mechanisms. One that is the sparse vector technique, which basically kind of tries to detect when we have flips. And then we have some private median mechanism that tries to release some information from these copies without compromising on their privacy too much. And I can kind of do the back of the envelope computation. Basically, the key idea is that advanced composition is in differential privacy is something that supports 1/epsilon² adaptive interactions provided privacy level of epsilon. So it's kind of a magic from differential privacy, and it gives this square root factor basically in the end. You can look at the this back of the envelope computation. Nothing very inspiring. It's advanced composition that does the heavy lifting in the back. And this differential privacy framework, we've seen that it is optimal in terms of the dependence on the flip number. And because of the optimality, because it is quite simple, it is extremely useful in applications. So for example, two applications where there are many others, but two examples I want to mention is doing robust count sketch that is in some strong sense optimal, and also producing dynamic graph algorithms that are adversarially robust, although there are some gaps in this context. Okay, so this was a differential privacy-based framework. Another framework that is based on difference estimators. And I think the first question that one asks when they see the sketch switching framework is why waste so much? Why maintain many copies that run from the beginning until the time they become active? So it seems wasteful. So this is kind of a framework that solves this problem. Instead of running many copies from the beginning, it runs copies at different granularities. And what's really nice about it is that it doesn't just shave off an epsilon factor for our setting, but it actually solves all open problems in the sliding window model. So I think it's the first example that we've seen of a result that kind of came up in the robust streaming literature, but actually solved something somewhere else. There are actually many examples of very interesting connections. For the rest of the talk, in the rest of the talk, we'll see several examples of this. Right. Yeah, I don't know if I have anything to say about. We discussed these frameworks and their limitations. And I guess the question that we may ask now is whether the flip number is always the right parameter. Is this the parameter that determines what the space complexity is going to be? So the answer is, I guess, if the answer was yes, I would have asked it. So the answer is no. So for example, distinct elements and F2 estimation, you can improve upon this square root of flip number, this square root of the length of the stream. You can do some slightly better polynomial in M. So for example, M to the 1 over 3 for distinct elements, M to the 2 over 5 for F2. And this is with Talia and with Krzysztof. But still, it's exponentially worse than static. In the static world, we have linear sketching, and this is basically the only techniques that work and are efficient. And there, the dependence in n is inside of the universe is just logarithmic. It's not polynomial. So it's an exponential separation. And this is kind of also a pretty simple proof. So the idea is that we use a ready-made sparse recovery solution that has for all guarantees that works with high probability for all inputs simultaneously. And so this is, and it also keeps track of the state of the vector even if we exit. So this is it's able to maintain the state of the vector in a way that it is always going to be correct when the frequency vector is sparse. And in the case where the frequency vector is dense, we have less flips than in the zigzag example that we've seen before. The number of flips is going to be at most m to the 2/3 instead of at most n. So this kind of trade-off gives something that is better than the square root of the length of the string. All right. So these were the frameworks, and we've seen that the frameworks are not always ideal. Sometimes we need algorithms that improve upon these frameworks, and we've seen perhaps. Okay, so I want to go back and mention that this is this exponential separation between static algorithms and robust algorithms for these two problems. I think this is like the big question of this field. The big question here. Okay, and for the rest of the talk, I want to tell you a little bit about several lessons that we've learned along the way. Well, we talked about sketching not being robust in this setting, but it turns out that sampling-based approaches are actually quite robust. So by sampling, I mean that we have a stream of updates that arrive one by one, and we sample each of these updates with some probability. It could be uniform probability. It could be something that is importance-based. We'll see that both of these options are actually robust. So I want maybe to quickly mention another question. It's not completely kind of a question of the streaming community, but more of the learning community, I would say, or geometry people also care about these kind of questions. or statistics. And the question is how many uniform samples we need from some data set for the sample to be representative of the data. Okay, then I'm probably going to ask what do we mean by representative? So the standard definition for representative is so we basically have a set of statistics, and we want each of the statistics over the sample to be a good approximation of the statistic over the data. So the fraction of the elements in the sample that satisfy the statistic needs to be more than epsilon fraction away from the fraction in data. This is called an epsilon approximation or uniform convergence, and it implies back learning. So different communities care about this. And well, in the static or oblivious setting, we know that the sample size that we need for being representative is the VC dimension of the set system or hypothesis class, or however we want to call it. And it turns out that sampling remains robust in the adversarial world. The same adversarial model as before, even a stronger adversarial model. It's called the white box adversarial model. That we'll say maybe a couple words about later on. But the point is that random sampling, just uniform sampling, remains robust in an adversarial world with some overhead. So we need to replace the VC dimension with another well-known dimension from the learning theory, which is called Littlestone dimension. And this is bound by VC times log of the length of the stream. So it's a pretty small overhead, and you don't need to switch techniques. It's the same technique, just with larger sample size. So we see here the sampling is kind of just works in the adversarial world. Yes? Length of the stream throughout the talk. It's not just uniform sampling, it's also true for important sampling. It's also robust for free. So this nice table was taken from the paper by Robert, Matthias, Shine, and Joe. And they have an impressive list of problems that can be solved using techniques that are kind of robust for free. So there are many problems in big data and machine learning that are solvable. I mean, where some algorithms just translate to the robust setting using important sampling-based frameworks. And well, this is kind of not very formal, but maybe someone may ask whether we can actually get a formal separation between kind of sketching type and sampling type techniques, or sampling type algorithms. And there actually is a beautiful work that kind of does this separation. This is a line of work by Amit, Manuel Steckel, Amit student, and Roim again. And they basically consider several models of randomness. So starting from the strongest model of randomness, this is random oracle. Basically, in the random oracle model, that I guess is more standard in the literature. It assumes that we have a fixed random string. It is always available to the algorithm. There is no storage cost associated with accessing this random string. But they also considered several other types of randomness. So random tape is basically we can generate fresh randomness with any given with any new update in the stream, but we need to pay to store it. It's not like it doesn't just stay there forever. And another weaker model of randomness is random seed, which is we have access to randomness in the beginning, and that's it. And the weakest model of almost weakest model of randomness that I consider is what is called the pseudo-deterministic streaming algorithms. So by pseudo-deterministic, I mean that given a specific input sequence, the output sequence will always going to be the same up to with probability, except for with probability delta. So it's like probability 99%. It's going to be always the same output. So apparently there are some problems where this pseudo-deterministic model is stronger than the deterministic model. This is not one of them. And there is a separation between all of these randomness models. So back to this discussion about sketching versus sampling type techniques. So what would you say looks like a sketching type technique? So it's a technique that, in sketching, we generate a random matrix in the beginning, and then we don't use any more randomness. So this is random seed. And sampling type technique?
Random tape.
Yep. So for this specific problem, we have formal separation between random seed and random tape. And also the other two models. Yes?
Sketching is random oracle. Why is it random? Don't you need? I mean, in a sketching, where do you store?
Oh, yeah. This is randomness and beginning, and it costs to store it. It's not random.
Oh, but when you do a sketching, or you
yes, I mean, yeah.
charge the algorithm for storing the random bits of the sketching matrix?
I mean, I think it's reasonable to assume this. So yeah, there actually is a problem where kind of sketching time algorithms are strictly worse than sampling type algorithms in this robust regime.
In one of the results that you mentioned, the sketching with the four-wise independence, you don't need to store the matrix, you just need to store the seed for the four-wise independence.
Yes.
That's why it's a low space algorithm. Otherwise, like the matrix itself is
right. So when I mentioned the Alon Matthias Segedi, so they just generate a seed, which is for the sketching matrix, which is small because they just need four-wise independence, not to remember all of the entries of the matrix. Okay. Yeah. Speaking about separation, so this is so robust graph coloring. Adversarially robust graph coloring is also a problem where we have some good separations. So in the static case, we have the beautiful specification technique that gives us optimal delta plus one coloring in a closed to linear space, in semi-streaming space. In the adversarial robust world, we don't have this free lunch, unfortunately. We either have to pay an extra delta in the space or lose an extra factor of delta in the number of colors. It can these lower bounds are known to be almost tight. There is some small gap remaining, but also we have a separation here between adversarial robust and deterministic. So if we want, for example, semi-streaming space, we actually need an exponential in delta in the maximum degree number of colors. So we have a delta separation, which for a very natural problem. So the problem that we've seen here, which is missing item finding, is kind of semi-artificial. But I mean, graph coloring is certainly a natural problem. All right. I think we are short on time, so maybe I'll just say that there are some interesting lessons about white box versus black box adversaries. So far we discussed black box adversaries, except for the result about uniform sampling, about random sampling, which actually works also in the white box world. By white box, I mean that the adversary doesn't see just the outputs of the algorithm, but actually its whole internal state at any given time. And still the algorithm needs to provide outputs that are accurate for the function over the string.
For white box, you have to flip coins on the fly, right? You cannot tell to flip all the coins at initially.
I think. So this is unsurprisingly, this is a harder setting. So for example, here we can prove that that FP estimation, that F2 and F0 are hard. So we can prove lower bounds here, unlike in the black box setting. And there are some kind of like weak, kind of near linear upper bounds. And even then, you need to work hard to get them. You need some cryptographic assumptions. But it's kind of, I think it's kind of unsurprising that it's hard, but there are some non-trivial things that you can do in this white box setting. And another, so this is the third lesson out of 4, and then the talk will come to an end, so we're pretty close to the end. I think one of the interesting highlights about this robust streaming model is that it has a huge number of connections and techniques from other areas. It's kind of a very fertile ground for kind of collaborations between different areas. So if you like streaming and you have friends that operate in other areas, this is a good place to look into interesting problems. So some techniques that are used in robust streaming and that are maybe not as commonly used in classical streaming come from differential privacy, cryptography, learning theory, adaptive data analysis, and this is a partial list. So I also mentioned that this technique of difference estimators that was developed as a framework for robust streaming actually found uses in solving an important open problems, an important open problem in classical sliding window streaming. So it's kind of very fertile in this sense. It also has a lot of applications. So I mean, these frameworks and the results that we've seen in the literature have a lot of applications in a variety of areas. It's quite interesting. And I mean, there's a lot to still be explored. So for example, I mentioned in the slide where about why we need this adversarial robustness, I mentioned some strategic players. So for example, the SEO when we communicate with Google. So this is kind of a game theoretic setting. It's not really an adversarial setting, and I don't think there's, at least myself, I haven't seen any literature that involves a lot of game theoretic assumptions. So I kind of have a theory that short-term memory in the brain is kind of a streaming algorithms. Maybe we're in kind of a streaming algorithm. Maybe I don't want to delve into it too deeply, but I think there are some connections between cognitive science and kind of making decisions in an interactive world with a bounded memory. Many other areas, reinforcement learning is another example. So this is if someone is looking for problems for like connections to different areas, this is a very, very good place to start based on what we know so far. And maybe the last lesson is kind of more personal, and it tells. And I just want to say something to students about kind of my personal history with this line of work. So do we have a German speaker in the audience?
Lion.
Okay, if we don't have.
Okay, so I can say it's a clever one. Yeah, so this is Riemann, the well-known Riemann that made the Riemann hypothesis. And he said that something along the lines of, give me a correct result and I will prove it for you. So I think the line of work on robust streaming kind of started this way. So the modern line of work on robust streaming. So I did mention, for example, the lower bound by David and Moritz for linear sketching, but kind of the modern line of work started by two people that had no idea about streaming or about learning theory, looking into like a learning theory question and making some success because it was actually some notions that were well known in the learning theory community, but we just didn't know about them. The two people are Elon Yogev and me. And based on this success, So there are two groups of people. So one group was just us. We just told David about this result, and David told Rajesh, and we were able to come up with this sketch switching framework. And I think that the differential privacy group was worked independently, so we probably saw this result and then figured out maybe something similar can be done in streaming, but kind of an unrelated result in sort of unrelated field started this area of robust streaming, which is kind of random, I would say. Yes, and I think we just had to have some positive related result about something to like kickstart this the work on robust streaming. So I think the history is kind of funny in this one. And yeah, I think this is what I have to say. Open questions. So the first two open questions are about the space complexity of adversarially robust streaming distinct elements, or F2. We actually have very poor understanding of lower bounds. So even for pseudo-deterministic algorithms, we don't have good lower bounds. And I think there are many open questions about kind of beyond worst case adversarial models. So the community started to look into beyond worst case models, but there's still a lot to explore. So for example, perhaps my favorite beyond worst case model that I would like to think about, if anyone else is interested, let me know, is, well, if we have a streaming algorithm that interacts with a streaming algorithm on the other side. So the adversary itself is like as strong as the algorithm. What can you do in this case?
So what if you assume that the adversary is just computationally bounded?
There are some results, some limited results right now, but yeah, it's also underexplored, I would say. Yeah. And yeah, so there are many models that one can come up with. I think the first one is my favorite. And I would say, I mean, we've seen that differential privacy is kind of a theoretical notion that became very successful in practice, that the big tech companies actually use differential privacy. And we also want the algorithms to be robust in practice, but we actually need to convince practitioners that our notions make sense, or come up with notions that they think make sense. So I think that like there is this open question of like talking with practitioners and actually making this a thing in practice and not just as part of the theoretical literature. And with this, I think I'll end the talk. Thank you.
I don't know if I missed it or you didn't mention it. What is distribution maintaining after?
Yeah, so it's kind of a model that I have in my head is, I don't know if it's like the right model to think about it, but I think the model that, and it's also relevant for I think for example dynamic graph algorithms. So I'm thinking of an adversary that has a distribution for any so a distribution over choices that it will make in any particular step in the future. And with each update of the stream, it can update this distribution, these future distributions, but not arbitrarily in some other way.
So you're saying after every update that it received, the distribution over its action would move by like at most.
Yeah, so the collection of future distributions changes in some bounded way.
Is there any lower bound known for F0 estimation depending on n, like log n?
Just a static lower bound, logarithmic.
Static, I think, is log n, so it's. I think Kane, Woodruff, Nelson is like log n model.
Okay, maybe. Yeah, I think it's logarithmic, at least for some of these problems, but yeah.
For F0. But basically,
oh, maybe for F2. For F2, I think it's logarithmic. For F0, it could be.
Do you know historically when this was said? Because there's a certain amount of irony. I mean, like, you know, Riemann, we have the Riemann hypothesis.
Yeah, I think no one told him that Riemann hypothesis is correct.
I think
Maybe it tells something.
self-humor. So,
I think toward the end of his life, given that he was alive only,
I think
unfortunately, only for 40 years. So
I think I've heard this book, like some translation of it.
I think around 1860.
It's one of the most notoriously hard problems. So.
I have a question about this like sampling versus sketching. So you showed this slide where there's some like separations for problems in like random seed versus random tape. I guess like, and it makes a lot of sense to me intuitively that having more randomness, like random tape, you can maybe have m bits of randomness and random seed here. I don't know, we want like logarithmic. But is there any like formal sense in which for adversarial robustness, like the amount of randomness you use, like there's some.
What do you mean by formal sense? I mean, this is a class that supports only. So this is a class that supports sampling, and this is a class that doesn't support sampling.
I see, yeah, but like the connection between, yeah, I mean, this is true for like separating sketching and sampling algorithms, let's say, but is there then like there's an intuitive connection to adversarial robustness?
Yeah, it's not something that, yeah, I mean, I don't have a formal definition for sketching type versus sampling type that is better than this. But I think this is a reasonable definition. I mean, I think it's quite interesting to kind of compare these two models.
Yeah, but I guess
this is exactly what they support.
Random tape, is there a problem that we know, like you can do adversarially robust streaming in one but not the other?
So this is the only problem where we know this kind of separation. It doesn't mean that it doesn't exist for other problems. It's just the only problem where we know this explicitly.
I see, and this is like there's a, okay.
Maybe, I don't know, maybe in graph coloring, given that the separations, maybe they already give. So this kind of separation would maybe separate. Yeah, so I don't, yeah, so this is the only problem with the
All right, cool. So let's thank. This brings us to the end.